Okay, so today we will talk about the attendance problem in section 11.7. 11.7, yeah. So as we say, actually in in chapter 11, almost all the questions, if you want to solve the questions, almost for the first of all, you should consider its partial derivative. First of all, you should consider the partial derivative and to check which way you should. I mean, it depends on the question. It depends on the question. But first of all, you should consider partial derivative almost. And here it's the same. We want to find the local maximum, local minimum, and the saddle point of the function. So let's recall the single variable case. Now, for this question, it has two variables. But for the single variable case, f of x, for example, x squared, if we want to find its local maximum or local minimum, then as we know, first of all we should consider its critical number. But when we say it's critical number, when we say the critical number, you should consider its derivative. So consider its derivative, then we consider there are two cases. First one is its derivative is 0. Second one is its derivative does not exist. If we say x0 is the critical number of a function, then there are two cases. But we will use if we want to use second derivative test to find its local maxima or local minima, then we focus on this case. Yeah. And actually, if for this function, you will see actually we don't have this term, right? For its derivative, it must exist. So actually, for its critical number, actually we don't have this term. We just have this term, right? And now, if we want to use the second derivative test, we will focus on this case. Its first derivative equals 0 under the assumption. Then we check its second derivative. If its second derivative is positive, then it's like the concave upward. Then, as we say, it's of the form concave upward. For its graph is concave upward. This one, so it has the local minimum. And its second derivative is less than 0. So for its graph, it's like this one, concave downward. And the concave downward, so it's the local maximum. Okay, so even for this function, it contains two variables, but they are related. It still has some results which are similar in this one. Okay, but so as we say, it's single variable case. So now for the original problem, if it contains two variables, then let's see what's the difference. As we say, we have the corresponding result, right? Here is single variable is critical number. So now for the function, if it contains two variables, then we consider critical point of the function. And for the function critical point, if x0, y0 is the critical point, then what does it mean? We still have two cases. First one is we consider its partial derivative, like this one. But it has two variables, so we have partial derivative by x or partial derivative by y. Partial derivative by x or partial derivative by y. And if we say it's critical point, then this one you should be careful. I mean, both of them should simultaneously hold. Both of these two equations should simultaneously hold. Okay, so partial derivative by x equals 0. Partial derivative by y also equals 0. Both of them are 0. Otherwise, another case is corresponding to this case does not exist. But when we say does not exist, just one of them does not exist. It's enough. Just one of these two partial derivatives does not exist is enough. One of them does not exist. This one. It means the critical point. But for this function, it's polynomial form. even in x or in y, it's polynomial form. So when you consider its partial derivative, it must be of the polynomial form. So it must exist. So actually, for the critical point, we don't have this case. We just have this case. Actually, when you consider critical point, it's just this case. Okay. And we use the second derivative test to solve this question. So it's something like this one. I mean, under the situation 1, for the point x0, y0 is satisfied these two equations, then we will check its local we will check if it has local maxima or local minima or saddle point. And how to check it? We should check the second derivative, like this one, second derivative. But it has two variables. So when we say check its second derivative, we should consider the determinant. Its determinant. And its determinant is defined by this way. Second derivative by x, second derivative by y, and the second derivative by x, after that by y, and here is by y, and by x, x0, y0. Okay, but as we know, actually for this one, if both of them are continuous, we know that the result says that they are the same. If both of them are continuous function, then actually they are the same. Anyway, so check it, and for its determinant, if it's positive, then we could say more, but it still depends on its second derivative. And we will talk about the detail later. And if its determinant is less than 0, then it's saddle point. So it's just what we say in class. Okay, yeah, so I just review some, and now we could check each all. Okay, so now let's see. As we said, the first of all, we should check its partial derivative by x and the partial derivative by y. And the partial derivative by x, so if we say partial derivative by x, then we will view y as a constant. And then if we consider partial derivative by y, then view x as a constant. So now we could write down the function. So first one, the function, view y as a constant. So here x cubed is derivative is 3x squared. Uy is constant, so its derivative is 0. Subtract 6x, and the constant is derivative 0. This one. And this time view x as constant, so its constant derivative is 0 plus 3. Put it down 3y squared. Subtract constant is 0. Derivative is 0, and then this time is 6y. This one. And simultaneously, both of them are 0. So both of them are 0. To check x, y, to check the s0, y0, So we should check its solution. And for this time, we take out the common number 3x. Then we still have x subtract 2. And here, take out the common number 3y. Then we still have y plus 2. This one. And if it's 0, then it means that x equals 0 or 2. And if it's 0, it means that y equals 0 or negative 2. This one. Okay, so now we could check its local which point it has the local maxima, minima, and the saddle point. But before that, as we said, you should check its determinant. So if you want to check its determinant, you should consider partial derivative. So partial derivative by, so this time, so you should consider this one, and this time it means that for this function, you should consider its partial derivative by x. So partial derivative by x, so it's 6x. So it's 6x subtract 6. And partial derivative, for this one, it's partial derivative by y. Its partial derivative by y is equal to 6y plus 6. And this term, fxy, it means fx. After that, we consider partial derivative by y. But partial derivative by y, then view s as constant, so it's 0. And then fys means this one. So for this function, we can say it's partial derivative by x, so by is constant, so it's 0. It's 0, this one. Okay, so now we could check dxy. So dxy is 6x subtract 6. Second derivative by x here, second derivative by y here, and the fxy is here, fys is here, so it becomes 6x subtract 6 times 6y plus 6. This one. This one is our dxy. Okay, and as we say, we will focus on the critical point. Which kind of critical point? Both of them are equals 0 simultaneously. So simultaneous. So for this term, it means that s must be 0 or 2. And for this one, it means that y must be 0 or negative 2. So we have 4 cases. So first one is 0, 0. Second one is 0, negative 2. Third one is 2, 0. The last one is 2, negative 2. This one. Okay, so now let's see for each one. So for the first case, first of all, check its determinant. So its determinant d0, 0 is determinant 0 subtract 6 is subtract 6 times 0 plus 6 is 6. So it's negative 36 is less than 0. Less than 0 means that 0, 0 is saddle point of capital F. If it's less than 0, it means that it's a saddle